Okay, so the mission of this whole thing is how can we use modern infrastructure to make the red team's job harder? So as you don't know, the red team is the guys that are trying to break in and test out your security. And what's modern infrastructure? So infrastructure's gone a long ways. So it used to be buy a box, put it online, install the operating system, patch it, and everything else. And nowadays it's all DevOps, so it's infrastructure as code. We push a button, we get a VM, we get a container, some other infrastructure turned on. That container might live for a couple of minutes, the VMs might live for a couple of hours, couple of days. But what about if we have things that are actually on bare metal, actual physical infrastructure? How can we secure those, and how can we take some of those techniques from modern infrastructure and use that for bare metal? Okay, so a red team, what's their typical way of going about doing things? For those of you who've seen this before, this is a kill chain. If you can kill something in the red team's operation, you can successfully prevent them from doing their job. So if you're a red teamer, first thing you're doing is reconnaissance. You're taking a look at the system that you're going to break into. You're doing active and passive scanning of the targets. You're doing sweeps across the network space. You're passively listening to network traffic, trying to identify the interesting targets, what targets are out there, what ports are open, what vulnerabilities are on there, and then you're actually going and exploiting those. You're going and you're hitting the vulnerabilities. You're trying to actually break into those targets that you found. Once you're on it, once you're on the system, then you want to escalate your privilege. You want to try and get root. You want to try and get administrator privileges so you can take over the system, get onto the information, use that computing resources. And then once you're in that network and you've got yourself a foothold, you want to go left and right inside the network. You want to go and exploit other systems within within the environment. Then it's okay, why did you break in the first place? Are you doing a denial of service? So maybe you're going to shut down the systems or overload the network. And then you're going to try and get data, you're going to extract data off of the network because you find value in that. Maybe you can sell it, you can make some money off of that. So this is the chain they run through, and me, as protecting the systems, if I can go in and I can stop them at any one stage going down here, I can successfully stop this attack. So a lot of companies, a lot of teams, they go, okay, how can we go through? Can we stop one of these? Can we stop multiple of them? What can we do to slow it down? If you can make the red team's job harder, exponentially harder in any way that doesn't cost you exponentially amount of computing power or personnel time, great. So we're going to keep your eye on this on the kill chain here. We're going to go through and figure out how we can use modern infrastructure to sort of kill the red team here. Okay, first idea. So in the VM world and the container world, like what I talked about, VM companies start them up. Ideally, they live for a couple of hours, a couple of weeks, a couple of days. Containers nowadays live for minutes and hours. But what happens if we can take bare metal and if we can start up a physical machine with the idea that it's only going to live for a couple of days. It's going to live for a couple of hours. And at the end of that time, the machine goes away, it's repurposed, the disks are scrubbed, the firmware is reflashed, and it's brought back to completely baseline configuration with new keys and everything. So if we do that, if we set up a machine and we set up our cluster of machines, our full environment, how can we hurt the red team on their kill chain? Well, we're going to hurt them on lateral movement because they're going to break into a machine. If they find a vulnerability and they get into that machine's only going to live for 2 hours. So maybe it takes them an hour to break into it. Great, now they're going to have an hour to try and do lateral movement, to do left and right and break into other parts of your environment. Same thing with pulling data out. They're going to have a limited amount of time to go through, do that privilege escalation, and pull data out of the network. So the next question is, well, how can we do this? How can we go and set up and automate and use modern infrastructure to build something like this, to set it up so that any system we turn on immediately is going to die after a couple of hours? Okay, so the next part of it is, how can we go and every time we start up a new server, the new server is somewhere new. We give it a different IP address, we put different keys on it, we run different services on it. For the network, for the red team, they're going out, they're looking across the network. Where they once didn't see a server in the IP address space, 2 hours later, there might be a server, right? So any scanning that they're doing of the network is going to be invalid 2 hours later because they're going to scan some network space, not see anything there, but then we're going to go and pop up a server there a couple of hours later, and bingo, they're not going to see it until they go back and rescan that whole IP address space. Rescanning the IP address space slows down the red team. It's going to take them longer to go and get onto our systems. Same thing on the lateral movement, right? If we're going through and we're moving things around behind their back. Okay, so how can we do that? We'll get that in a second. Okay, so that brings us to our first proof of concept. So we're using some code from HashiCorp, from Terraform, Infrastructure as a Service. So Terraform, people use Terraform before? A couple of people? Yeah, I'm always surprised. Like if I talk at cloud conferences, everyone's used it. I talk at security conferences, and it's sort of a little bit less. So you're going to see a lot of automation infrastructure as code technology here in this presentation. So the whole idea behind Terraform is you write your deployments as configuration files that list out how you want the environment how you want to describe the environment that you want. So on the right here, we've got some configuration that describes a resource. It's called web server. We have some SSH keys that go through and use to set it up. A host name, so it's a host name, it's a format, so it's web-00 through the number of web servers we want to run. The plan and the facility, so facility is the data center to run it at, the plan is the hardware type, and we run Terraform, and Terraform takes this configuration file. And Terraform is actually infrastructure agnostic, so you can point it at AWS, you can point it at Azure, you can point it wherever you want, and it'll go through and spin up the environments. Here, we're pointing it at a bare metal cloud provider packet, so it goes and it turns on a physical machine. So in this environment here, we're going to turn on 10 machines. They're all going to be configured, different host names, different set of keys, and the rest of this, if you go into the GitHub, you can see the whole environment, but it goes through, sets up a web server, and sets up that full environment. Let's go through, and we're going to start a little video, and we can see one of these in action. So what I've done is I've cloned the GitHub page. And I don't know if I can make this bigger. I hadn't thought about that. No, I'm not sure that really helped. But basically what it's doing is we're taking a configuration file, we're setting up the number of servers to run, the sample file, and then we're going through initializing, which pulls down the plugins, so it knows which clouds to connect in. It's got the plugins for those clouds. We're going to plan. It's going to take a look and tell us what it's going to do and how many servers it's going to deploy. So the way infrastructure as code works is it takes a look at your plan file and compares to what you're running in the cloud. So if it sees a difference, it then goes and makes up that difference. So if for some reason your cloud is supposed to be running 10 and only 9 are running, it's smart enough to go and realize that it needs to go turn on one additional one. So here we go. We've started up. It's actually making a call out to the data center. It's requesting however many machines is. I think I'm doing 3 machines here. Requesting the infrastructure. It takes about 90 seconds for the hardware to be deployed and made available. So in 90 seconds, we've got access to 3 brand new physical machines. And then we go through and we do the installation. We install the software on top of it. It's all automated through. So I'm not going to go through run through the whole thing, but you get the idea. Okay. So the end result is 2 minutes later, we've got our infrastructure deployed, it's up and running, software's completely brand new installation. Now what happens if we take this into a loop and we go through and we kill the oldest one and then rerun Terraform? It's going to continuously replace all the machines that die out. Each new machine that comes online is going to have a new set of keys, new set of IP addresses, so the red team's going to have a harder time finding it. So if you're interested in this, this proof of concept's available online. You can go through and run it yourself. Okay, but the next part of the question is, who controls the life cycle of the servers, right? We need some way of going through and killing the servers. We can't trust the server itself to kill itself, right? We can't just put a timer on there, because what happens if the red team gets on that machine? They're going to know that there's a timer going off in 2 hours, and they're going to go through and spend the time to try and turn off the timer so the server doesn't self-destruct. So do we need a central authority? Well, if we build a central authority, then we're going to have something for the red team to go after, and they take over that central authority. We've defeated the purpose of all of this. Can we do some sort of distributed quorum where they decide amongst themselves, and if they don't hear back from one of the machines, they know it's gone rogue and kill it. And so this part is still a research item. I'm still trying to think up good ways to solve this one, but interesting part to consider. Okay, so next thing, let's go back to our list of how we can slow down the red team. So key management. So keys are used, encryption's used to go and get access into the machines. It's used to encrypt data, but here we're going to use them for authentication and authorization. So if we can go through and move our services, the services running on the machines constantly around, and if we can change the keys that you need to access those services and constantly rotate the keys, if any key is compromised, it's only going to be around be able to be used for a fixed amount of time, a couple of hours. And then if we can get the access control down to each of a pair of the consumer and the the consumer and the service that's using the key, and set up each key for that single pair, we can greatly reduce the red team, because they're going to find a key. A key is not going to be used for more than one service and one client that's requesting that service. So that's going to give them very limited access to our environment. And same thing, what happens if we're constantly changing those keys? So how can we do this? So the next part of the next proof of concept we put together is running a service mesh. So as we go through and we spin up this environment, we set up a service mesh, and what a service mesh does is it goes through and it registers all the services that you're running on your host, and it puts together a sidecar, another process. In the container world, it's another container. In the bare metal world, it's another process on the physical machine. And it sits there and intercepts the requests go through the sidecar, and the sidecar is responsible for authentication, authorization, and encryption of the data that's going back and forth. So the second proof of concept, which we'll actually see a full demo of this one towards the end, is in this proof of concept we go through and we create a fortune cookie service. Anyone remember the old Unix fortune command? It just spits out a random fortune. So what we've done here is I've taken that, made it into an unsecure service running on port 8181 that was bound to the public interface, that previously anyone could connect to it, no authentication, no authorization, and it would send back a fortune. So the problem is, not encrypted, no authentication, no authorization, anyone can go hit that. So instead what we do is we take that fortune cookie service, we unbind it from the public interface and bind it to the loopback, run the sidecar, and then the sidecar sits there. It receives the request. It has to be an authentication, it has to be an encrypted request, it has to have the proper keys, and then it forwards along that request through the loopback to the actual service, gets the response and sends it back. And the service mesh is responsible for managing all these keys. It runs in a cluster environment, manages the keys, distributes the keys, rotates the keys, and then each key is the combination tuple of the client making the request, so in this case the fortune cookie consumer, and then the service that's providing it, so fortune cookie server. Okay. Okay, so next part of this. What happens if we move from IPv4 to IPv6? If we start going using a much larger IP address space, what's this going to do to the red team? What sort of impact is this going to have? So IPv6 addresses are much larger than IPv4. The address space is huge. You can get private IP address spaces. You can use it yourself on your own private network. And basically, they're disposable. You can use an IPv6 address once, throw it away, never use it again, and pick up and pick up another one. So what happens if we start running all of our services on IPv6? We run the service, we run it for 2 hours on that IPv6 address, service goes away, we bring it back up again, right, on a different IPv6 address. What does that do to the red team? Well, the red team is now scanning through this much larger address space. And where they previously didn't see things, we're going to be spinning services back up. Where they did see things, we're going to be spinning them back down, and then they're going to have to start back over again to try and keep up to date on where we are. So the RFC for IPv6 actually talks about this. It says, as a result, traditional services of remote TCP or UDP network scanning to discover open or running services on a host will potentially become less feasible due to the larger search space in the subnet. So pretty easy way, go through, switch over from V4 to V6 and start using disposable addresses. Now, obviously, if you do move to V6, you don't want to be sequential in your IP address assignment, right? You don't want to start going 1, 2, 3, 4, 5, 6. So you want to make sure you go through and assign it accordingly. You don't want to start using some of the techniques that people are using where they stick the MAC address in the IPv6 address in field, because then the red team's going to get knowledge about what your addresses are or what the systems are that they're going after. And then it also reduces the address space down because you're using some fixed values in there. Okay, so how do we actually implement this? What do we need to do here? So this is another proof of concept we put together. It uses BGP. So BGP is a routing protocol, a border gateway protocol, and Anycast. Anycast is a way of taking an IP address and sharing it across multiple hosts. So the idea is that you can have a pool of machines all using the same IPv6 address. Anycast does work with IPv4, but for this example, we're using v6. So we have a number of machines all sharing the same IPv6 address. So that's where the service is registered to. And they're communicating with their upstream router, registering themselves, making sure that the upstream router knows that they're running. To do that, you can use some open source software called Bird. Bird provides BGP routing in your whatever Linux distro you're using, and it talks to the upstream v4, v6 router. And it communicates out that this machine wants to participate in that IP Anycast address space. And so the end result is any request that comes in, the router goes through and it routes through to whichever machine it finds is the closest one. And then if a machine goes away, it dies. Remember, all of our machines have a limited amount of time. It goes away. The upstream router will notice that the machine goes away, that the updates aren't being sent through, and the machine will get removed from the Anycast pool. So this is some Terraform output you can see. Where a machine has been assigned with an Anycast IPv6 address. That one that ends in :1 is the IPv6 Anycast address in this example. One of the interesting things about IPv6 is, like, when you run a curl command, you need to put the v6 address into brackets there. And so the last one where it says server IPv6s, we've got 2 physical machines running IPv6. They have 2 different IPv6 addresses. So one is :7, the other one's :D, and they're both sharing that same IPv6 address, so the :1. So if we were to kill one of those and rerun Terraform, it would start up a new one with a different IPv6 address for itself, and then it would also register itself back onto the :1 address too. So you'd want to do this on outwardly facing services that you would have someone from the internet access. So they wouldn't know about the internals of the actual physical addresses of those machines. They would just access the Anycast address. Okay, so that brings us up to the proof of concept we put together for IPv6 BGP Anycast. So in this environment, what we do is we spin up multiple machines. They go through, they automatically write their BGP configuration file, the Bird configuration file, and they automatically register themselves with the router. So we extend the Terraform, so the Terraform goes and it runs, starts up the machine comes online, and new keys registers itself with the service mesh, and then also registers itself with the router, talking BGP. So the whole thing's automated. A couple of minutes, bingo, you got a new replacement machine up and running. And this is another proof of concept lab environment we run where we give students access to the physical machines. We set them up with environments, and then they go through and scale it up and scale it down to simulate the full environment. Okay. So any questions on the presentation so far, or any things that people, because I know we're in the way of lunch, so next I'm going to go through and we'll watch a demo of it in action. Yeah.
So you've done this in production?
So we haven't done this in production. So the part of production we're using a production bare metal cloud. So we split it up into 3 different proof of concepts to go through and identify it. And yeah, so right now we're going through taking a look at how would we conquer each one of the different aspects. And then I think the next step is sort of combine it all together and then run some sort of Metasploit or some sort of attack tool against it to find out how well it handles.
So does Terraform handle like session drain out? Like, let's say you're spinning up and down web servers and there's ignorance versus using a session, right?
Sure.
So
So Terraform doesn't do load balancing. So all Terraform is going to do is just going to spin things up to match the state that you want. So something like the BGP Anycast, it would go through and do the load balancing across all the systems, or the service mesh. So when a service goes offline, it would have to unregister itself from the service mesh, or the service mesh would notice that it's no longer there providing the services.
So I'm referring to the scenario where you're saying, oh, I'm just going to turn down my web server and run one down, right? The server may have sessions, live sessions.
Yes, yeah. So you need to, you'd probably spin up machines first before you kill them. So you want to make sure you always have extra capacity than under capacity, and then take that machine out of the rotation to drain off, and then let it go away. Yeah. So, yeah, your load balancing does need to have a little bit of intelligence. Any other questions before I go through and run through the demo here? Okay. So the demo, it's actually up on YouTube. So it's a demo I put together that is going to go through and showcase this example with the Fortune cookie service. So we're going to go through, we're going to see Terraform in action. We're going to go see the Fortune cookie service being registered and unregistered. I'm going to come around here so I can see better. Oh, actually, it's up on my screen too. So what we see here is 4 different windows. I'm going to go through and log into 4 different machines. Console is the name of the service mesh software. It's from HashiCorp. So Console, people have heard of Istio, and there's Linkerd. There are other service mesh implementations for different environments. The thing I like about Console is it's not dependent on a containerized environment, so you can run it basically on top of applications. So that little bit of JSON there is a description of the service that's running, and then we're just connecting to port 8181 to go just see an example of the Fortune cookie service running. There's 2 different JSONs we're looking at. One is called just Fortune cookie service, and the other one's called Fortune secure service. The secure service uses that sidecar to do the additional authentication and authorization of the request as it goes through. And you can see that it lists out the sidecar there. So what I'm doing is I'm turning off the unsecure one, and then I'm copying in the configuration file for the secure one. And then once that's going, I'm going to go and tell the Fortune cookie, or I'm going to tell the service mesh to reprocess the configuration files. So it's going to go through and it's going to reload and pull in the configuration files back. So now we can see that there are 2 services running on the service mesh. One is the sidecar process, and the other one's the Fortune cookie process. Okay, so now we're going to go to the next server, and we're going to go through and do the same thing. So the end result of all of this is we're going to have 3 Fortune cookie services running, each of them receiving connections on port 9191, which go through the sidecar process, which authenticate the user, handle all the encryption, and then we're going to go through and simulate killing them to show that we have redundancy going. Okay, so on the left there, we've got the sidecar process running, and then we're going to go to the next one. Oh, this is the consumer. So on the consumer side, it also needs to register with the service mesh because it needs to go and get the keys. So it goes and requests keys and is allocated keys based upon what it's allowed to do. And every time you start the service, you need to go through and tell it what the upstream connection is. So Fortune 9191, port 9191 is the encrypted service, and port 8181 is the unencrypted service. So we're going to run netcat, connect to port 9191, and that's going to show that we're running through the encrypted service. The beginning part of this demo, which I cut out, I go through, I do a little man-in-the-middle attack, where I showcase we can go through and we can do a TCP dump, and we can actually watch the packets going through, and we can see the unencrypted traffic running through. And so now, since we're running it encrypted, you can't go through and see it. The other interesting thing that a service mesh does is it keeps track and it does health checks of all the services. So what you'll see occasionally is there'll be a hit in the log file, even though no consumer is actually making the request, and that's because it's the service mesh going through and checking, making sure the service is running. Okay. So I'm going to speed up a little bit here. And so at this point here, we have spun up. We have, on the left there, you see it's the results of Terraform running. And we've got the 3 console servers running, and then we've got 3 Fortune Cookie servers running. And then we are going through and making connections to them to go through and see which ones are running. I'm going to just connect on a little bit further. Because I think the most interesting part is when we start killing them. Okay. Okay, so here on the lower left-hand one, I went and I shut down that one. And so the end result is we're going to have one fewer machine running. The service mesh is going to go through and detect that. If we keep on running the netcat commands, we'll see that the consumer is still able to make requests and get access to the infrastructure, even though it has no idea that one of those machines is now down, because the service mesh is totally abstracting out the which machines are needed and the machines behind the service. So the end result is you can go through and you can spin up, spin down, run it through the service mesh, and the service mesh is hiding all of that from the application using that service. Is it still running? Yeah. Okay. Still going through making requests. Oh, did I pause it? Okay. And now we're going to connect to the second one, and we're going to go through and kill it. So this goes back to the idea of, well, who's going to be going through killing the machines, right? There needs to be some good way of going through and making sure the machines die. So it pauses for a second because the service mesh hasn't noticed yet that that machine's offline, but now it keeps on running. And you notice the consumer doesn't really care. It doesn't have to go through a given address. It just gives the name of the service that it's looking for. It doesn't care. You're not typing in IP addresses. You're just saying, I want to talk to a Fortune Cookie server, as opposed to actually having to say, I need to talk to the service running on this IP address at this port. With the service mesh, you just say, I want the Fortune Cookie service. And now we've gone through and we've killed the last one. And now we can see that we get no response when we call the service. So the end result is, the idea would be, we've slowed down the red team through a combination of using smart infrastructure, through a combination of using Terraform, a console, a service mesh. We've been using a smart cloud provider, or you could use an AWS environment too, and just be constantly changing your infrastructure. I think it also is a great way if you have people that you've given access to, you don't know what they've done on the machine, and maybe if they changed it, you had some admin, he's no longer with you, you want to constantly be changing your hardware and refreshing it to the most pristine images possible. So that said, that about wraps it up. Happy to answer any questions, or if you want to try out some of these proof of concepts, like I said, they're up on GitHub. The links are on my slides. I can also get you some cloud credits too if you need some time on some of these clouds to go and play with it. Thank you.